We're now moving forward with 11.4, colligative properties. Here we're going to express concentrations of solution components using mole fraction and molality. Describe the effect of solute concentration on various solution properties, such as vapor pressure, boiling point, freezing point, and osmotic pressure. Perform calculations using the mathematical equations that describe these various colligative effects. Describe the process of distillation and its practical applications. And explain the process of osmosis and describe how it is applied industrially and in nature. So let's first talk about colligative properties. So the properties of a solution differ considerably from those of a pure solvent and pure solute. For instance, salt water tastes pretty nasty compared to regular water. Some solution properties depend on the identity of the solute, something like the acidity, the basicity, or its density. But there are properties that only really care about the solute concentration and not its identity. And these are called colligative properties. So they depend mostly on the concentration of the solute particles and not on the nature or the identity of the solute. So we're going to talk about vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. The units we'll be using here and there for concentration, just remember we have molarity, the big M, which is moles per liter, mass percent. Okay, we talked about that way earlier in the year or in the semester. Mole fraction and this should be molality, not molarity. So let's start with just a quick refresher of molarity. That's defined as the moles of solute per liter of solution, and the symbol is a capital M. Remember that it's a capital M. The problem with molarity is it's temperature dependent. So your volume of solution can change with temperature. If you increase the temperature too much, you might make your solution evaporate. Okay, we also have mass percent, which is grams of solute per over 100 grams of solution. Okay. Again, that can be altered by something like temperature. However, mole fraction is independent of temperature. So if you have some component A, its mole fraction is the moles of A divided by the total number of moles of all the solution components. So that includes your solute as well. So all the mole fraction, when you add up the mole fractions of all the components, it is going to equal 1. And then we have molality, not molarity, molality, with a lowercase m. And this is moles of solute per kilogram of solvent. So this is also independent of temperature. So we're going to go ahead and look at an example for calculating mole fraction and molality. So if we have antifreeze, it tends to be a mixture of equal parts ethylene glycol and water with some other things to prevent corrosion. And we want to start by finding the mole fraction and the molality of ethylene glycol in a solution prepared from 2.22 times 10 to the third grams of ethylene glycol and 2 times 10 to the third grams of water, so approximately 2 liters of each. So the first thing we should do for the mole fraction is figure out our moles of ethylene glycol. Well, we need our moles of both, so let's go ahead and find moles of both for mole fraction. Okay, so our moles of ethylene glycol, C2H4OH2, is going to equal, we have 2.22 times 10 to the third grams of it. And its molar mass, we have 1 mole of it per every 62.07 grams. So we have 35.8 moles of ethylene glycol. Actually, I'm just going to put EG for ethylene glycol because chemists are lazy and I am a chemist. Our moles of water, which we also need for mole fraction, we have 2.00 times 10 to the third grams. And we have 1 mole of water per 18.02 grams of it. So we have 111 moles of water. So then our mole fraction is going to be, which we use an X, so we say XA is equal to our moles of A divided by total moles. So this is now 35.8 moles of ethylene glycol divided by 35.8 plus 111. That's moles total. And you can see that the moles cancel out. So mole fraction is dimensionless. It's a ratio. So this mole fraction is 0.244. So that then means that our mole fraction of water would be 1 minus 0.244. So for part B, now we want molality, which is moles per kilogram of solvent. So as we can tell by the moles of each one, water here is going to be our solvent. We have more moles of water. It doesn't seem like it when we look in terms of grams. Well, we have more moles of water. So we're going to go ahead and call that our solvent and the ethylene glycol as our solute. And we already have our moles of ethylene glycol. And then to then get kilograms of water, we're going to go to that 2.00 times 10 to the third grams. And we know there's 1 kilogram for every 1,000 grams. So this is 2 kilograms of water. So our molality then is equal to 35.8 moles divided by 2 kilograms. We have a molality of 17.9 molal. Yes, it's molal. Molal, molal, however you want to say that. All right, here's another example. Calculate the mole fraction of solute and solvent in a 3.0 molal solution of sodium chloride. So since it's 3.0 molal, we have 3.0 moles of sodium chloride for 1 kilogram of water. So we need to go ahead and take this 1 kilogram of water and turn it into moles so that we can get the mole fraction, because all we have is sodium chloride and water. So we have 1 kilogram of water. And we know we have 1,000 grams per 1 kilogram. And 1 mole of water per 18.02 grams. And that gives us 55 moles of water. So now our mole fraction of sodium chloride, we'll start by doing that one, is equal to 3 moles divided by 55 plus 3 moles. So that's 3 over 58. And that gives us 0.052. And if we can just go ahead and do this again for water if we want. That's 55 moles divided by 55 plus 3 moles. And we get 0.95. And if we add those up, okay, we have 2, let's see, 0.052, just to do that, redo that there, 0, 0. We get 1.002, it's 1, okay, so we're good there, that checks out. And the only reason that it might seem a little bit more is just from rounding. And rounding between converting the kilograms of water to moles and then doing calculating the mole fractions themselves. All right, another example. Intravenous infusion of a 0.556 molar aqueous solution of glucose, density of 1.04, is part of some post-operative recovery therapies. What is the molal concentration of glucose in this solution? So let's rewrite the molarity as 0.556 moles per 1 liter of water, or liter of solution, actually. Technically, it's not water, but liter of salt. And we know molality is moles per kilogram. So we actually need to get the mass of the water in the solution. But our solution is more than just water. It's water and glucose. So let's get the mass of the solution first. So we have 1 liter of solution, and we were told its density. That's a big hint that we can't just go ahead and say this is 1 liter of water. We can remember there's 1,000 milliliters per 1 liter. And our density, we have 1.04 grams for every 1 milliliter. So this gives us 1.04 kilograms of solution. So this is the mass of the water and solution. So that means that we need to subtract the mass of glucose that's in solution. So the mass of glucose is 0.556 moles of it times its molar mass, 180.2 grams per 1 mole of glucose. So we have that there's 100.2 grams, or 0.1002 kilograms. Oh, I did skip a little step here. Let me just add 1 kilogram per 1,000 grams. So then now we have our mass of glucose that's in this 1.04 kilograms of solution. So our mass of water then is equal to 1.04 kilograms minus 0.1002 kilograms. So then we get 0.9398 kilograms of water. So now we can get the molality. So we have 0.556 moles of glucose per 0.9398 kilograms. So we go ahead and type this into our handy dandy calculator. And I get a molality of 0.592 molal. Alrighty. So now let's talk about vapor pressure. If you take some non-volatile solute and put it into a pure solvent, you lower the solvent's vapor pressure. So if you think about it, now you've added something that's floating around, and for your solvent to evaporate, it has to be able to go to the surface. So now you have something in the way of it getting to the surface, so it can't break through as easy. So this causes it to evaporate slower and having a lower vapor pressure. So vapor pressure lowering is a colligative property. We don't care what the solute is, we just care how much of it there is. So if you remember back, we talked about liquid-vapor equilibrium. If we put a liquid in a closed container, we get this equilibrium of vaporization and condensation at equal rates. So the vapor pressure, if you remember, of the liquid is the pressure exerted by the gas phase molecules. More gases, the higher the pressure. So we have to be able to have solvent molecules at the surface to vaporize. But if we put some solute in there, like I said, we're going to decrease the surface area available for those solvent molecules to vaporize. So now, since less of them can evaporate or vaporize, the rate of which this happens decreases, but the rate of the condensation stays the same. So what ends up happening is now we have less going into the gas phase, meaning less gases pushing down onto the liquid, lowering the vapor pressure. So we have what is called Raoult's law, and this is the partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure component multiplied by its mole fraction. So P solution, which is the vapor pressure of the solvent in solution, is equal to X solvent, which is the mole fraction, times P naught solvent. P naught meaning, or P star, whatever you want to use. Your book does P star. I don't know why that's showing P naught. P star solvent, which is the vapor pressure of the pure solvent. So let's look at an example. Let's find the vapor pressure of an ideal solution with 92.1 grams of glycerin and 184.4 grams of ethanol at 40 degrees Celsius. We're told the vapor pressure of pure ethanol is 0.178 atm at 40 degrees Celsius, and glycerin is basically non-volatile at this temperature. So the first thing we need to do is get our moles of each component, because remember, P solution is equal to our partial pressure of our solvent times P star of the solvent. So we have 92.1 grams of glycerin. I'm just going to do a capital G. And the molar mass of this, we have 1 mole of it for every 92.094 grams of it. So we have basically 1 mole of glycerin. For our ethanol, we have 184.4 grams of ethanol. And 1 mole of ethanol for every 46.069 grams of it. So this gives us 4.000 moles of ethanol. So now we can get the mole fraction of ethanol. So that is equal to 4 divided by 1 plus 4. I'm just not worrying about decimal points right now, which is 4 over 5, which is 0.800. So our pressure now, our P solve, is equal to our X solve, 0.800, times P star solve, which we were told 0.178. And we end up getting 0.142 atm. Remember that mole fraction is unitless. So now let's talk about distillation. This is a process where you can separate solutions made of components that have very different vapor pressures, so different boiling points. And so we separate them by selective vaporization. So what you do is you have your mixture of your 2 liquids, for instance, some component A and B, and you're going to heat it where A has a much higher vapor pressure. It boils a lot easier. So it leaves the system as a vapor, and then it goes to a cooling cis part where it's able to condense back into a liquid, and then it drips down into a collection area where we're able to collect it back as a liquid, and now we've separated the 2 components. Very common in laboratory and industrial settings. For those of you that are going to be continuing with your chemistry journey, whether you're chem majors, bio majors, etc., when you go on to organic chemistry, you will do lots of distillations. One example in industry is fractional distillation. This is used to separate crude oil components. So this is what a laboratory distillation setup looks like. You've got your mixture of some A and B. Sometimes you can do it with multiple mixtures too. And you use the temperature here, the thermometer here, you're actually able to monitor the temperature and see where your liquid boils. And then your vaporized part comes up here, and then it gets into this this guy here where it's able to cool down. So it's literally a condenser, and what these arrows are is actually water that's going in from the sink and coming out. So it's just continuously circling to keep that cool water jacket to help the gas now condense back into a liquid. And then it goes and it drips down into a receiving flask. This is what a setup looks like for crude oil. So there are these massive setups here. Okay. So you take your crude oil, you put it in what's called a fractionating column. So you take your crude oil, it goes in the bottom here, and it heats up, and the lighter gases, the lightest ones go out the top, and then gasoline is next, and then you can see the different oils. Kerosene, diesel oil is much heavier, it tends to be dirtier than gasoline, fuel oil, and others. So based off of this difference, the ones at the top, the higher they are, that means the lower their boiling point, the more volatile they are. They can flow and ignite easier, whereas the larger molecules towards the bottom have a higher boiling point. They're not very volatile. They don't flow very easy. They don't ignite easy as well. So let's now talk about boiling point and freezing point and how we change that with solutes. So if you have a solution, you dissolve some stuff in some water, you raise the boiling point. So it boils at a higher temperature than the pure solvent because you've lowered the vapor pressure, right? So now there's less of those solvent molecules vaporizing. So it takes more energy to get them to vaporize at the same rate. So we have what's called the boiling point elevation, or delta TB, and we'll look at the equation for that later. It's the difference in the boiling point of the solution and the pure solvent. So you can solve for this, and then you can predict, you take that delta T, you add it to the original boiling point, and then you get its new boiling point. Now with a solute, a solution freezes at a lower temperature. So that solute, so remember, to freeze, we have to cool those particles down enough where they're able to start interacting with each other, and then they eventually form into a crystal or non-crystalline lattice where they're just kind of vibrating in place. But as they're trying to get closer together and they're moving slower and slower, you've got these solutes getting in the way, so then your solvent is not able to freeze as easy. So this is used in, for instance, salting roads in the winter when it snows. Not so much in California, but especially on the East Coast, they do a lot of this. They salt the roads and it melts the water. Or if you've ever added salt to ice water, you might notice that the ice melts, but it gets really, really cold because you've lowered the freezing point of your water, so now it can get colder than 0 degrees Celsius. So this is called freezing point depression, and this is delta TF. Same type of thing with the boiling point elevation. We calculate delta TF, subtract it from the original freezing point, and now we can predict our new freezing point. So these are both a direct result of lowering that vapor pressure. Remember, boiling occurs when the vapor pressure equals atmospheric pressure, and that vapor pressure is directly proportional to temperature. We add in a solute, we lower the vapor pressure. So now we need a higher temperature to get that vapor pressure to equal atmospheric pressure, increasing our boiling point. So these are both colligative properties, boiling point elevation and freezing point depression. They depend on the concentration of the solute, with the solute concentration in molality. So if I have 1 mole sucrose and 1 mole ethylene glycol, those solutions are going to boil at the same temperature. I don't care that it's sucrose, I don't care that it's ethylene glycol, I just care that I have 1 mole of solute. So to find these changes in boiling point or freezing point, these are our equations here. Delta TB equals MKB, where M is our molality, and delta TF equals MKF. So KB and KF are constants for boiling point elevation and freezing point depression. Your book, table 11.2, has some values of them for certain substances. Here's a screenshot from your book showing you some KBs, and for some reason it's calling the freezing point one. That should be an F, not a T. I don't know why it says KT. This is straight out of the book. But you can see the different values depending on what your solvent is. So let's look at an example and the steps to solve it. So assuming ideal solution behavior, what is the boiling point of a 0.33 molal solution of a non-volatile solute in benzene? So we need to first identify our molality of the solution, figure out how much it changes, and then we can calculate our new freezing point. So we need to first now get delta TB, because we have our molality. So that is equal to KB times M. And we look in our table to find benzene. Now we see boiling point, its KB is 2.53. So we have 2.53, and those units are degrees Celsius per meter, or per molal, or times inverse molality, times our molality of 0.33 molal. And so this gives us a delta T boil at 0.83 degrees Celsius. This is not the final boiling point. This is the change, the delta T. So now our temperature, okay, is equal to the pure solvent's boiling point, which we can look that up, and we find that it's 80.1 degrees Celsius. That's in that table also. And we're going to add 0.83 degrees Celsius. That's how much we've raised the boiling point. And we get 80.9 degrees. So we've raised it a little bit, 80.9 degrees Celsius. So here's another example. This one has a lot more steps. Boiling point of an iodine solution. We're told we want the boiling point of a solution that has 92.1 grams of iodine in 800 grams of chloroform, assuming that the iodine is non-volatile and the solution is real. So we first need to take this mass of iodine, get it to moles, get the molality, then we can calculate our change in boiling point, and then the new one. So we have 92.1 grams of iodine, of I2, and we need to go ahead and look up its molar mass to get the moles of it. So I'm going to grab my phone here, look up molar mass of iodine, because I don't feel like calculating it myself. Make sure it's the molar mass of I2, because iodine is diatomic. So the molar mass of I2, according to PubChem, we have 1 mole of iodine. Oops. Come on, pen. There it goes. 1 mole of iodine for every 253.8 grams of it. We'll just go ahead and do it that way. And so then that gives us around 0.363 moles of I2. The next thing is to get our molality. So we have 800 grams of chloroform, which is 0.8 kilograms. So now our molality is equal to 0.363 moles over 0.8000. And so then we get 0.454 molal. And now we can go ahead and get our change in boiling point. So our delta TB equals our KB. And so we're looking at chloroform as our solvent. And its KB, according to our table, is 3.63 degrees Celsius per molal times our molality, 0.454. Those guys cancel. And we get 1.65 degrees Celsius. So now our temperature is equal to our original boiling point, which is 61.26 plus 1.65, and we get a final temperature of 62.91 degrees Celsius. Okay, so here's an example. Rock salt or calcium chloride or a mixture is used to melt ice. So this is kind of a picture of the process happening, adding it, and then the ice starts to liquefy into water because now it has a lower freezing point. So it's not going to be frozen at 0 degrees Celsius. It's going to be much lower. So now here's an example. Assuming ideal solution behavior, what is the freezing point of a 0.33 mol solution of a non-volatile electrolyte solute in benzene, as described in example 11.4. So to start off, we have our molality, and we can use that to figure out our change in the freezing point and then calculate the new freezing point. So these are the freezing point, boiling point problems are very similar. So our delta TF is equal to Kf times M. So we look at the table, and the Kf is equal to 5.12 degrees Celsius per molal times the molality of 0.33. And we get 1.7 degrees Celsius. So this is how much our temperature is decreasing. So now our temperature, we look at our original freezing point temperature is 5.5 minus 1.7. The freezing point is now 3.8 degrees Celsius. So just here's some de-icing happening using freezing point depression. In A, they're de-icing the roads, and they're also used to help de-ice the wings of aircraft because ice on the wings can be detrimental and deadly. All right, so this section of this part of the section talks about two phase diagrams, or phase diagrams for a solution. So we're looking at what happens when you add a solute to solution. So you can see the dashed lines represent the aqueous solution, and you can find the delta TF and delta TBs as well. So you can see those boiling points change and our freezing points change. Yeah, that's about it there. You can just see the change. I thought it's kind of a nice thing to see. All right, now we're going to start moving on to osmosis. Kind of a funny, somewhat little anecdote. My boyfriend doing his history PhD, and he was reading this paper, and it actually talked about osmosis of people, put in the title, and I was so angry. I was like, that's not osmosis. So now he teases me about it. Okay, so let's talk about what a semi-permeable membrane is. So this is a material that will only allow select molecules or ions to pass through that have a certain size, shape, polarity, charge, whatever factor. So semi-permeable membrane is kind of like a bouncer at a club. They only let through who they're told to or who they want to. You can't bribe them, though. All right, so think of a membrane, a semi-permeable membrane that only allows solvent molecules to permeate and not solute. So your solute cannot. Semi-permeable membrane is can separate some pure solvents from a solution. Okay, so you've got pure solvent on the left. Okay. Pure on the left, and then solution on the right. So what happens is the solvent molecules can go across the membrane in both directions. But the concentration of that solvent is higher in the pure sample. So this is my pure side. So what happens is those coming from the pure side to the solution actually go a lot faster than the reverse. So it looks more like that. So you end up with this net transfer of solvent molecules from the pure solvent to solution. And this is diffusion driven. And this process is called osmosis. So what happens also as an outcome is that the volume of solution is going to increase on that solution side. So now as we are transferring more of that pure solvent over, its volume's going down, and the solution volume has gone up because we're adding more of the extra solvent. So now this is increasing the hydrostatic pressure. You have more liquid, so it's increasing that pressure. But now because you have this extra pressure pushing down on your solution, more of that solvent is going to transfer back to your bulk pure solvent. So when you get to a point though where the rates end up being equal, okay, you might still have these unequal volumes, but the rate of solvent transfer is equal. The bulk transfer stops. So now we're at equilibrium. And we have what's called osmotic pressure, and we abbreviate that with a capital pi sign. So here's a much better drawing showing what's happening here. So this flow of solvent, like I was saying, during osmosis makes this force. Okay, giving us osmotic pressure, and that's the pressure that is just barely enough to prevent the osmosis from occurring. So now we don't have any actual transfer. So the concentration, though, for this equation, so the osmotic pressure is equal to mRT. So we've been looking at molality. Now we are going back to molarity. So our concentration is big M molarity. R is our universal gas constant, and we're going back to the 0.08206 liter ATM per mole Kelvin, and our temperature is in Kelvin. So let's go ahead and look at an example real quick. And we're going to calculate osmotic pressure. So assuming ideal solution behavior, we want to find the osmotic pressure in ATMs of a 0.30 molar solution of glucose in water that is used for IV infusion at body temperature 37 degrees Celsius. So we know that big pi is equal to mRT. We've got M, we know R. We need to go ahead and take this T, add 273 to it to make it Kelvin, so we have 310 Kelvin. So our osmotic pressure then is equal to 0.30. Let's go ahead and put it this as moles per liter times R, 0.08206 liter ATM per mole Kelvin times 310 Kelvin. Kelvins cancel, moles cancel, liters cancel, left with ATM. We get 7.6 atmospheres. Now, if you were to add pressure to the solution side greater than the osmotic pressure, this gives you the process called reverse osmosis, or RO. So this is where now you're pushing those solvent molecules from the solution back to the pure solvent. So this is very commonly used in water purification. You can actually get reverse osmosis systems for your home. They create actually a lot of wastewater. It tends to be about 25% or so of the water produced is actually pure water, whereas the other 75% is waste. If you have an RO system at home, for instance, I have one for my fish tanks. I direct my spout of the wastewater if I'm trying to make some RO water to my plants or to the grass outside, because it's still fine for that. It's just not, it doesn't, so RO water generally doesn't have really many dissolved ions or things that can affect the fish. So this is just kind of showing the process of reverse osmosis. Here's a couple also systems. A small scale, that's kind of what you might have in the house. Nowadays you can get even smaller systems. And B, large scale, which these are often used in military or in humanitarian efforts. Osmosis plays a huge role in our body systems and red blood cells. So our red blood cells are basically semi-permeable membranes. So they're water permeable. If you, for instance, have too much, of whatever solvent of solute in your red blood cells, whatever it is, be it salt or whatever, water is going to flow into them to try to dilute it. Okay, solution. So if you are trying to do like an intravenous solution, you have to make sure they are what's called isotonic, which is B here. They have the same concentration of salts or whatever you need in your body. You need it to be the same. So if you have a hypotonic solution, what ends up happening then is water goes into hypotonic, sorry, not hypertonic. So if you have a hypotonic solution, that means it ends up having a lower concentration than your blood cell. So that means now water is going to flow into the blood cell to try to equalize these solutions, and it ends up making the red blood cells expand, which can potentially cause them to burst and kill you. If your solution that is injected into the body is hypertonic, so that means it has a lower concentration than what's in your red blood cells, then the water can leave the cells in a process called crenation and makes them shrivel up and die, making you potentially die as well. So very important for those of you going into the medical field to be using isotonic solutions for your patients. Now, we can use our colligative properties to determine the molar mass of solutes. So we can use our freezing point lowering and osmotic pressure to do this. And we're going to look at some examples to show how it's done. So the way it tends to go is you take some known mass of a solute and you add it to either a known mass of solvent or you make a known volume of a solution. Then you go and measure its colligative property, either the change in freezing point or osmotic pressure. And then you can use that to calculate its concentration. So either in molarity or molality. So for instance, molality from the freezing point depression is equal to delta TF over KF. Or from osmotic pressure, it's equal to pi osmotic pressure over RT. That should be a capital pi, not a lowercase pi. You can use that to then get your number of moles of solute present from the concentration, and then calculate the molar mass by taking those moles moles you just found, dividing them into your grams of solute. So let's look at an example here. We have a solution of 4 grams of a non-electrolyte dissolved in 55 grams of benzene, and it's found to freeze at 2.32 degrees Celsius. We're going to assume ideal solution behavior and find the molar mass of this compound. So the first thing we have to do is take that freezing point and find delta TF. Okay, so that now delta TF is equal to 5.5. You can look that up in the table for pure benzene, minus 2.32. And our delta T is 3.2 degrees Celsius. And now we can find our mole concentration. We look up our KF, and we have our delta TF. So now our molal concentration is equal to delta TF, which is 3.2 degrees Celsius, divided by 5.12 degrees Celsius over molality. So that gives us molality up top. So now our molality is equal to 0.63 molal. Now we can use that to get our moles of compound in the sample. So we have 0.63 moles for every 1 kilogram of solution. And we're told that, or not of solution, but of solvent. And we're told our solvent, we have 55 grams of benzene, And that is the same as 0.0550 kilograms. So that tells us we have 0.035 moles of solute. And now we can get the molar mass, because we have 4 grams of it, which we were told from the start, divided by 0.035 moles. And that gives us 1.1 times 10 to the second grams per mole. Didn't need that extra room. All right, another example. A 0.5 liter sample of an aqueous solution containing 10 grams of hemoglobin has an osmotic pressure of 5.9 torr at 22 degrees Celsius. Assuming ideal solution behavior, what is the molar mass of the hemoglobin? So we're starting with our osmotic pressure, and we're going to use that to get our molar concentration. So remember, osmotic pressure uses molarity. So just kind of write that down to remind us. Equals MRT. And then from the molar concentration, we can get moles of hemoglobin in our sample and then get its molar mass. So one of the first things we need to do with this osmotic pressure we're given is change it to ATMs, because we're given it in torr. So we're going to go ahead and take this 5.9 torr, and there is 1 atmosphere per 760 torr, and that gives us 7.8 times 10 to the negative third ATMs. So now we have our correct units of pressure. So solving for molarity from our osmotic pressure equation, molarity is equal to the osmotic pressure over RT. So then our molarity is equal to 7.8 times 10 to the negative third ATM divided by 0.08206 liter ATM per mole Kelvin times 295 Kelvin. This 22 degrees Celsius plus 273 gives us 295. So liters, oh, sorry, liters don't cancel, liters stay. ATMs cancel, Kelvins cancel, and we end up, when you do 1 over liters over moles, that gives us moles per liter. And so then we get 3.2 times 10 to the negative fourth molar, or moles per liter. And so now we can take that to get our moles of hemoglobin. So I'm going to go ahead and change this from putting big M to moles over liter, moles per 1 liter of solution. And we were told we have a 0.500 liter sample of solution. So 0.500 liters. Liters cancel. So we have 1.6 times 10 to the negative fourth moles of hemoglobin. And so now we can get our molar mass. We have 10 grams of it. Oops. 10 grams per 1.6 times 10 to the negative fourth moles. And that gives us 6.2 times 10 to the fourth grams per mole. So now let's talk about some colligative properties of electrolytes. So colligative properties, remember, are directly proportional to the concentration of solute particles. We do not care what those particles actually are. So if we have a given concentration, electrolytes have a greater effect on the colligative properties than non-electrolytes because they break apart and now you have more things floating around. So if I take a mole of glucose and put it in water, I get 1 mole of solute because it's a non-electrolyte, it stays together. But if I take a mole of sodium chloride, which is a strong electrolyte, it's going to break apart into Na plus and Cl minus. That gives us 2 moles of solute particles, so more stuff to get in the way. So we also have what is called the Van't Hoff factor, and this is the ratio of solute particles in solution to the number of the formula units that are dissolved. So there's predicted and actual Van't Hoff factors. We really only care about the predicted. For sodium chloride, I should be predicted to be 2 because we make 2 ions. For glucose, it's 1. For calcium chloride, when this breaks apart, we get 1 Ca plus and then 2 Cl minuses, so we get an I predict of 3. For sodium phosphate, that gives us 3 Na plus ions and 1 PO4. So that guy is a, oh my gosh, why am I spacing on the name right now? Polyatomic, there we go. So we get an I of predicted of 4. And there are actually differences between some predicted Van 't Hoff factors and measured ones. For instance, if you look at magnesium chloride there, you see a really big difference from predicted of 3 to sorry, I'm looking at the wrong one. Magnesium sulfate is predicted to have a Van 't Hoff factor of 2, but it's actually measured to be 1.3. So for strong electrolytes, sometimes they're lower than expected. And so what this implies is incomplete dissociation. So it makes us go, wait, so is not everything dissolving? What's happening, though, is the attraction between the cations and anions prevents a small amount of the ions from behaving completely independent of each other. So you might form some ion pairs. We have what's called an effective concentration. That's also called activity. And it tends to be less than the predicted concentration of ions in solution. Much less of an issue when we have dilute solutions because you have more water to get in the way. That's really all you need to know about that. I'm not going to make you do anything with it. This is just kind of showing how you may not have total complete dissociation. For instance, you see this KCl here still kind of attracted to each other. And I don't know if you can hear that rumbling, but Sprite has decided to lay on my stomach while I'm trying to lecture and record and play with my necklace as well as purr her head off. And chew on my microphone. Hey, stop. Okay, so let's go ahead and look at an example with the freezing point of a solution of an electrolyte. So we're told the concentration of ions in seawater is approximately the same as that in a solution containing 4.2 grams of sodium chloride dissolved in 125 grams of water. Use this information and a predicted value for the Van 't Hoff factor to determine the freezing temperature of the solution, assuming ideal solution behavior. So the first thing we need to do is go from grams of sodium chloride to moles of sodium chloride using its molar mass. I'm going to assume you guys are good with that now, and this gives us 0.072 moles of sodium chloride. The next part we need to do is figure out how many moles of ions are made. And we know using the Van 't Hoff factor, the predicted one, that we make 2 moles of ions for every 1 mole of sodium chloride. So then that tells us we have 0.14 moles of ions. So now we can get our molality because we have our moles in 125 grams of water. That's 0.125 kilograms. So our molality is 1.2 molal. Oh, that's not a box. We're not done yet. So now we can go ahead and find our change in freezing point. So our delta TF, so going back to the table from earlier, for freezing point depression, for water, KF is equal to 1.86 degrees Celsius times inverse molal times 1.2 molal. So our change in freezing point is equal to 2.1 degrees Celsius. So now our new freezing point, we're going to go back. So now our freezing point is equal to 0 degrees Celsius, which is the normal freezing point of water, minus 2.1 degrees. We get negative 2.1 degrees Celsius as our new freezing point.